we're now going to introduce the mathematical background to electromagnetism and special relativity, specifically looking at four vectors, which is simply a way of combining space-like and time-like quantities. So the simplest example of a four vector is the position space four vector, and I'm going to write it as follows. X superscript alpha, and I'll come back to the point about a superscript in a moment, is equal to X, Y, Z, and CT. Alpha goes from 1 to 4, and we call this a contra-variant four vector. I will explain how contra-variant and covariant vectors are derived and how they're defined formally at the end of the video. If you're not interested in the mathematical details, it's entirely fine to skip that. So we call that the contravariant vector. You will often find that people write it as CT, comma, X, Y, Z, and in that case they'll often say that alpha goes from 0 to 3. It's just a different notation. The final physics is entirely identical. So let me introduce what I've already referred to, the covariant vector, X subscript alpha, which is X, Y, Z, and minus CT. Again, alpha goes from 1 to 4, and we call this covariant. So in Cartesian reference frame, this is in Cartesian coordinates, this kind of transformation is quite simple. The only difference, as you can see, is a change in sign in the time-like component. And then we introduce a rule which says that when you want to make a scalar product between two four vectors, you can only do that when you have opposed indices. In other words, the scalar product is the sum over alpha of X subscript alpha X superscript alpha. So you can only do a sum when you've got one lower and one upper, one subscript, one superscript. And if we do that contraction, we often actually save time and space by omitting the sum sign. So we say that you have X subscript alpha, X superscript alpha. That is defined as including a sum. You imply the sum. And that's known as Einstein notation, or the Einstein summation convention. And that's equal to, of course, X squared plus Y squared plus Z squared minus C squared T squared. And in the previous video, we referred to that as the interval. And we noted that it was invariant under Lorentz transforms. And by analogy, you can think about the dot product between two three-dimensional vectors as being invariant under a rotation. So the length of a vector doesn't change when you simply rotate the coordinate system. That's a very good analogy for what's happening here, is that this interval is invariant under the Lorentz transform, which is a rotation amongst space and time-like components. So, how do we transform between covariant and contravariant indices? Well, we're going to use what's called a tensor. It's a second-rank tensor. Fundamentally, it's a matrix. So we write the following. We say that X subscript alpha is equal to G subscript alpha subscript beta X superscript beta. And you'll notice now, of course, that because we've repeated the index beta and because they are opposed, we will then sum over beta. And we write this tensor G, which is known as the metric, as the following: matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. So you see that, of course, that matrix just has the effect of flipping the sign of the fourth component. Let's write out that transform for X alpha explicitly. So we've got 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. I really should put my brackets in after I finish the matrix, because that way I know how big to make them. And that's going to act on the components of X superscript beta, which is X, Y, Z, and CT. Now, when we do the matrix multiplication, you take a row, so 1, 0, 0, 0, multiply it onto a column, X, Y, Z, and CT. And of course what we get is just X, because that's the only component that is non-zero. For the next line, 0, 1, 0, 0, we're going to pick out this Y. The third line, the 1 is going to pick out the Z. And the fourth line, the minus 1, is going to apply to the CT. So let's put all of those in. So the second row, we pick out a Y because it's 0, 1, 0, 0. The third line, we pick out the Z. And then the fourth line, we have a minus CT. So let's put the brackets in there. So that's how that transformation works. It's simple matrix vector multiplication, which is something that you should be familiar with by this stage. We can, of course, write the Lorentz transforms in terms of a tensor. And the tensor is defined as follows. If we assume that we are going with between two frames S and S prime, where S prime has a velocity v is equal to v 0, 0 relative to S, and then we write the Lorentz transforms R as gamma 0, 0 minus beta gamma, and I'll define those terms in a moment, 0, 1, 0, 0, 0, 0, 1, 0, and then minus beta gamma 0, 0 gamma. And we define beta as v over c, notice that's v, the scalar value, and then gamma is equal to 1 divided by the square root of 1 minus beta squared. R may look just a little bit different to the way that you often see the Lorentz transforms written for position and time. That's because when we typically write the Lorentz transforms out explicitly for position and time, as I did in the previous video, we write time, not CT. So that's the only difference there. And of course you can rewrite R if you have a velocity along a different axis or a general velocity, but this is the most easy way to write it out. Now let's just think about applying this transform and think about the nature of R. We're wanting to go from X, which is our original position time 4 vector, and we're going to have components beta, and we're wanting to generate the coordinates in X prime, which is going to have index alpha, and we're needing to apply the matrix R to that. Now we have to have R having the first index as a superscript alpha, and then the second index has to be a subscript beta, so that we can contract across beta and we can do the matrix vector multiplication. So in this case we would say that R alpha beta is a mixed tensor, where the tensor G that we introduced just above was purely covariant. These are not important details, I'm just explaining them in case you're interested. So that tells us how to transform any 4 vector we choose. X is just an example, there are many other 4 vectors in between reference frames using the Lorentz transforms. Two important 4 vectors that we do have to think about. First of all is the differential. So what would happen if we looked at d by dx alpha? We actually write that as d subscript alpha. It's a covariant matrix. And in terms of the components, we find that that's actually d by dx1, d by dx2, d by dx3, and d by dx4. So please note, this is covariant, but we're differentiating with respect to the contra-variant variables. And so if we write that out in terms of x, y, and z, and t, then we get d by dx, d by dy, d by dz, and 1 over c, d by dt. The other 4 vector that you often encounter is the momentum energy 4 vector, p alpha, which is just given as px, py, pz. Those are the space-like momentum components, and then e over c. But you have to be careful. We define p, the vector, as gamma m times the velocity, and e is equal to gamma m c squared. This is an electromagnetism course, not a particle physics course, and not a special relativity course or a mechanics course, so I'm not going to go into any more detail, but that's just to give you a little flavour of where we are. So at this point, you can stop watching if you want to. What I'm going to do now is I'm going to discuss a little bit more about why we call these vectors covariant and contra-variant. So, if you're still with me, wanting the mathematical detail, here we go. We're going to assume that we're transforming between reference frames, as always. So the coordinates are going to go from x to x prime, and we assume that you can write that as x prime is equal to some function f of x. That's standard and easy to see. Then we would say that a contravariant variable, or a contravariant tensor, four vector rather, sorry, is one which transforms as follows. So we're going to label it as A, and so we're going to say that A prime and its alpha component is going to be defined by dx prime alpha, dx prime alpha by dx beta acting on A beta. And let's just pause a second and take note of what's going on here. So d by dx superscript beta is actually a covariant quantity, and so covariant contracts with contravariant. This effectively has a lowered index, which we contract there, and then the alphas combine here, so that's fine. A covariant 4-vector, and of course you can extend this to tensors, but you have to add in extra things. We have B prime is going to have a subscript alpha, and that's defined as dx superscript alpha by dx primed superscript beta b beta. That's the wrong way around. That should be x beta up top, and it should be an x primed alpha down below. That's better. And again, we can just take a look, and we have an upper index on the x beta and a lower index on the b, and then d by dx upper alpha is actually a covariant quantity, and therefore has a lowered index, which corresponds to b prime. You have to be very careful with these kinds of things. So that's the simple distinction between covariant and contravariant vectors. It's just which way up that differential is. Let's just make a brief note. What we're interested in is noting about, whoopsie, that was not what I meant to do. Let's come back to where I was. What we're interested in is invariance. So if we're going to say the following, let's say that we're going to write b dotted with a is equivalent to b alpha a alpha, and really that needs to be invariant because it's a number, and when we change between reference frames, numbers shouldn't change. Therefore that must equal b primed alpha a primed alpha. Now let's substitute in. So b primed alpha is dx superscript beta by dx primed superscript alpha b subscript beta, and then a primed superscript alpha is dx primed superscript alpha by dx superscript beta a superscript beta. Actually, let me change the betas here and into gammas because I want them to be different variables because they're different sums. There. And the alphas stay because the alphas belong here. Okay, now let's just rearrange the order of those. Because we're keeping the implied sums, we can just rearrange. So what we see is dx superscript beta by dx primed superscript alpha, dx primed superscript alpha by dx superscript gamma, b subscript beta, let me rewrite that beta clearly, a superscript alpha. Now notice, this is simply the chain rule. So we've got x primed alpha, and therefore we can actually rewrite this as being dx superscript beta by dx superscript gamma, and that is simply equal to delta beta gamma. So it's a delta function because it's only one if beta and gamma are the same. Therefore, we can now write delta superscript beta subscript gamma b subscript beta a superscript gamma is equal to, and let's just sum, let's say, over gamma, then what we have is b subscript beta a superscript beta, which is of course exactly what we wanted. So this shows that the scalar product of two 4 vectors is invariant under Lorentz transforms. Well, under any appropriate transform actually, but we're concerned about the Lorentz transforms. And what that's demonstrating is that this definition of co- and contra-variant vectors satisfies that need for invariance. So that's the end of the mathematical detail. In the next video, we'll move on to thinking about 4 vectors that are relevant to electromagnetism. And then after that, we'll think about how we can formulate Maxwell's equations in a form that is uninvariant under Lorentz transforms.